Today on Think Cosmos, we are going to stand on the edge of an ancient Martian lake and stare at freckles in a rock. Tiny rings, dark specks, needed guide status, patterns so small you could cover several of them with a single grain of sand. On Earth, textures like these often form when microbes eat their way through mud at the bottom of a lake. On Mars, they might be the strongest hint of ancient life we have ever seen. The rock is called Cheyava Falls. The core drilled from it is called Sapphire Canyon. And in September 2025, NASA scientists stepped up to a microphone and used a careful electrifying phrase. Potential biosignature. Bond. Not proof. Not a fossil microbe under a microscope, but a chemical and textural fingerprint that looks eerily like the ones life leaves behind on Earth. Tonight we are going to unpack what Sapphire Canyon really is, what Perseverance saw, why scientists are excited, and why they are also cautious. Segment 1. The stage. Jezero Crater and an old river delta. First, the setting. Setting. Jezero Crater is a 45-kilometer wide impact basin near the Martian equator. Billions of years ago, water poured through a river valley called Neretva Vallis and spilled into the crater, forming a fan-shaped delta and a lake that may have lasted hundreds of thousands of years. Where rivers meet lakes on Earth, you get mud, layered sediment, decimated by layered sediment, organic material, washing in, minerals that lock in the chemical story of the water column. That is why NASA chose Jezero as the landing site for Perseverance back in 2021. If Mars ever hosted surface life, a long-lived lake and its surrounding delta are some of the best places to look for the traces. Perseverance is not just a camera on wheels. It carries a drill to collect rock cores. It has a catching system to seal those cores in tubes for a future Mars sample return mission. And it has a suite of instruments built specifically to hunt for signs of past life. Segment 2. Meeting Cheyava Falls. In July 2024, Perseverance rolled into a region on the western lip of the crater that mission scientists call Bright Angel. Bright Angel is an ancient river channel that once carried water into the lake. There, the rover spotted a meter-long slab of reddish mudstone with white bands. The team nicknamed it Cheyava Falls, after a waterfall in the Grand Canyon. Up close, Cheyava Falls did not look smooth. The Watson camera, the close-range imager on the rover's arm, revealed strange speckles and rings on the rock face. Some were small dark nodules. Others were pale spots with darker rims around them. The team gave them informal names. The simple dark dots, like sprinkled seeds, became poppy seeds. The ringed spots with bleached centers and darker outlines became leopard spots. On Earth, structures with that look often form when chemicals move through wet sediment, sometimes guided by microbial activity. Perseverance scientists knew they had to drill here. Segment 3. Drilling Sapphire Canyon. Later that month, the rover extended its coring drill and bit into Cheyava Falls. It cut out a thin cylinder of rock and slid it into a metal tube. That core was given a formal sample name, Sapphire Canyon. From that moment on, Sapphire Canyon became one of the most precious objects in the solar system. Inside that tube is a time capsule from about 3.2 to 3.8 billion years ago, when Jezero's lakebed mud was still soft and water still flowed across the crater rim. Perseverance cannot crack the tube open. Instead, it studies the rock at the drill hole and surrounding surfaces using its arm-mounted instruments. The goal is to learn as much as possible now, while also preserving the sample for a future return to Earth. Segment 4. The detective team, Sherlock, Watson, and PIXL. 3 instruments are at the heart of the Sapphire Canyon story. First, Watson, the camera we already met. It takes detailed color close-ups of the rock textures. Second, Sherlock, which stands for Scanning Habitable Environments, with Raman and luminescence for organics and chemicals. SHERLOC is a laser-based spectrometer. It can spot organic molecules and map minerals at very fine scales across the rock surface. Third, PIXL, the planetary instrument for X-ray lithochemistry. But PIXL uses an X-ray beam to measure the chemistry of tiny spots on the rock, down to elements like iron, phosphorus, and sulfur. Together, these tools let scientists match texture, chemistry, and organic signatures almost grain by grain. Segment 5. What they found inside the rock. When the Sapphire Canyon data were finally pulled together and analyzed, a very specific picture emerged. First, the rock itself. Cheyava Falls is a mudstone, made of fine-grained clay and silt laid down in the ancient lake. That is already a good sign. On Earth, mudstones are excellent at preserving traces of life, because fine sediments can quickly bury organic matter and protect it. Next, the chemistry. SHERLOC detected organic molecules in the mudstone. The signals show carbon-containing compounds mixed into the clay-rich layers. These are not the first organics ever found on Mars, but they are notable because of where they sit. PIXL and SHERLOC also found that the rock hosts minerals like vivianite and greigite. Vivianite is an iron and phosphorus mineral that often forms in water-rich, low-oxygen environments where organic matter is present. Greigite is an iron sulfide mineral related to magnetite and pyrite. On Earth, greigite is often linked to microbial processes in sediments and to chemical gradients that microbes can exploit for energy. The spectrometer saw these minerals concentrated around the leopard spots and along pale mineral veins that cut through the rock. Those veins are made mostly of calcium sulfate, the product of water moving through the rock after it formed and leaving minerals behind. Inside and around those veins, the team saw the ringed patterns. Dark rims, bleached centers, organic signals, and those iron-bearing minerals all clustered in the same place. On Earth, that mix is often associated with microbes consuming organic matter and changing the chemistry of their surrounding. Segment 6. The Leopard spots as potential biosignatures. So what exactly are these leopard spots? In the simplest terms, they look like tiny reaction fronts frozen in rock. Imagine a lake bottom where mud rich in organic matter is piling up over time. Water flows through the pores in that mud, carrying dissolved chemicals. If microbes are living there, they may use the organic carbon as fuel and perform redox reactions involving iron, sulfur, or phosphorus. Those reactions can cause new minerals to form in rings or nodules around the zones where chemistry is changing fastest. Later, when the mud turns to rock, those zones become patterns of different color, hardness, and composition. The Leopard spots in Cheyava Falls line up with this kind of story. Dark rims where iron-rich minerals like greigite and vivianite are concentrated. Alia interiors that seem bleached compared with the surrounding mudstone. Organic molecules and subtle differences in element ratios tied to the same features. None of this proves life. But the combination of textures and chemistry is very similar to certain microbially influenced structures in Earth's sedimentary rocks. That is why scientists are willing to use the phrase potential biosignature. Segment 7. Why? Scientists are still cautious. Mars has burned us before. We have had methane plumes that later looked more ambiguous. We have had meteorites with debated microfossils. We have had landers and rovers detect organic molecules that turned out to be produced by non-biological chemistry or complicated surface reactions. So the Perseverance team is being careful. For every biology-friendly explanation, they are working through non-biological alternatives. Could purely chemical reactions between organic matter and minerals in the mud have created the leopard spots without microbes? Could changes in groundwater chemistry, temperature, or pressure form these minerals and textures over long time scales without any biology? Could the organic signals be from simple carbon molecules delivered by meteorites and later altered? On Earth, vivianite and greigite often sit in environments where bacteria are active. But in principle, Mars could host different pathways. The Nature paper and NASA briefings emphasize this. Potentia biosignature means a pattern that could be biological, but that has not yet ruled out all non-biological options. Segment 8. Why? Sapphire Canyon is still a big deal. Even with that caution, Sapphire Canyon stands out. First, it ties together several lines of evidence in one place, a lake environment with long-lived liquid water. Fine-grained sediments capable of preserving delicate structures. Organic molecules embedded in the rock. Mineral vines that show water move through the rock after it formed. Iron and sulfur minerals that, on Earth, often track microbial processes, and microscale textures that look like reaction fronts or fossilized nodules. Second, the rock is old. The mud that became Sapphire Canyon was likely deposited more than 3 billion years ago, when Mars was warmer and wetter and Earth itself was home only to microbial life. If life ever arose on Mars, this is exactly the kind of age and environment where we would expect its traces. Third, the sample is already cached. Sapphire Canyon is not just a picture and a spectrum. A physical piece of that mudstone is sealed in a tube and sitting on the Martian surface, waiting for a ride home. If Mars sample return flies in the 2030s, that core could end up in labs on Earth, under electron microscopes and high-resolution instruments, far beyond what Perseverance carries. Segment 9. Mars sample return and the politics of a rock. Here is where science meets budgets. To turn potential biosignatures into a clear answer, scientists need to examine samples like Sapphire Canyon in Earth laboratories. That is the goal of Mars sample return, a joint plan by NASA and the European Space Agency. The idea is to send a lander, a small rocket, and an orbiter. The lander would collect the cached tubes, load them into the rocket, and launch them into Mars orbit. The orbiter would grab the sample container and bring it back to Earth. It is a complex, expensive mission. Recent cost estimates have climbed into the $10 billion range, and NASA has faced pressure to cut or reshape the program. Sapphire Canyon changes that conversation. When agency officials talk about Mars sample return now, they can point to a specific core and say, "This rock may contain the clearest traces of ancient life we have found on another world." Do we want to leave it there, or do we want to bring it home? Segment 10. What happens if it really was life? Imagine that 15 years from now, scientists slice ultra-thin sections of Sapphire Canyon and peer at them with powerful microscopes. They see microscale mineral textures that match known microbial structures from Earth. They measure isotopes the ratios of heavy to light versions of elements like carbon, sulfur, and iron, and find patterns strongly consistent with biological metabolism. They compare all the non-biological models, and they fail to reproduce the full set of observations. At some point, the community might agree that the simplest explanation is ancient microbial activity in Jezero's lake mud. What would that mean? First, it would tell us that life is not unique to Earth, that at least once in a neighboring world with similar early conditions, chemistry crossed the threshold into biology. Second, it would show that microbial communities can emerge, thrive, and disappear on a planet that later loses its surface water. That has big implications for exoplanets and for the long-term future of life in the universe. Third, it would shift our view of Mars itself. The red planet would no longer be just a cold, dusty desert, but a world with a documented biological past, even if that life is long dead. Mars would become the first place where we discovered life twice. Once here, on our own world, and once there, in a mudstone core called Sapphire Canyon. Segment 11. What if it was not life? There is another outcome we have to be ready for. Suppose detailed studies of Sapphire Canyon and other samples show that all of the textures and minerals can be explained by exotic but purely chemical reactions. Suppose the organic material turns out to be simple, non-biological carbon. In that case, we still learn a lot. We would get a deep look at how complex geochemistry can become on a young planet. Without biology, we would refine our understanding of what counts as a reliable biosignature and what does not. And we would prove that it is possible to be misled by Earth analogies, which is a valuable warning for the study of other worlds. Either way, the sample will teach us something profound about how planets work. Segment 12. The bigger mosaic. Sapphire Canyon is a star of the current story, but it is not the only piece. Perseverance has collected more than 24 cores from different layers of Jezero's history. Some come from lava flows on the crater floor. Some come from deltaic mudstones in other regions. Some come from rocks that record later, drier climates. On top of that, the Curiosity rover in Jezero Crater has already reported organics preserved in ancient mudstones and seasonal methane variations in the atmosphere. Orbiters have mapped clays and sulfates across the planet. Each measurement is one tile in a mosaic. Sapphire Canyon may be the brightest tile so far because it pulls together organic chemistry, minerals, and textures that all whisper the same word: habitability. Habitability. But the truth about Martian life, or the lack of it, will come from weighing all of these clues together. Segment 13. Closing, staring at freckles in the dark. As we end this episode, picture Perseverance parked in the bright Angel Channel. The lake is gone. The river is dry. The air is thin and freezing. But on the rover's arm, SHERLOC, PIXL, and Watson are still working, still mapping faint signals in ancient mud. Thousands of kilometers away, in meeting rooms on Earth, scientists argue about Leopard spots and vivianite and greigite, and whether chemistry alone can sculpt patterns that look so much like biology. And in a metal tube lying on the Martian surface, a slender core of blue-gray rock waits, silent, for someone to decide whether it is worth $10 billion and a decade of effort to bring it home. We do not know yet if Sapphire Canyon holds the first confirmed fossils from another world. What we do know is this: for the first time, the search for life on Mars has narrowed down to a concrete object we can point to. Not a vague idea. Not a blurry signal. but a specific rock in a specific place, with features that on Earth would make any geobiologist drop what they are doing and book a flight. Whatever the final answer turns out to be, that alone is a remarkable step. We are no longer just asking, was there life on Mars? We are asking, what exactly happened in this one patch of mud, at the bottom of this one lake, billions of years ago? And that is how big cosmic questions become real science. One rock. One rock. One core. One canyon of sapphire. In the red dust. This has been Think Cosmos.